we do a lot of review in this chapter as well. We are reviewing how to identify linear functions. We're reviewing how to graph lines. And then we also review some other types of graphs and functions as well, but it does focus a lot on linear. So I first have, just as a review of what a relation is and what a function is. So this first part is just going to be vocabulary and being able to identify what's what. So I'll highlight a few things too. So a relation, whenever we talk about a relation is just a set of ordered pairs x, y. So you can also think of a relation as being a relationship between x and y. Okay, so even if your variables aren't x and y, a relation is a relationship between two quantities. Okay, so then a function is a specific type of relation. So a function is a relation in which each element of the domain, and the domain is the set of all of the x values, is paired with exactly one element in the range, the set of all y values. So the key there is where it says exactly one. I know it's italicized. But in a function, you cannot have an x value paired with more than one y value. If that happens, then it's not a function. It's still a relation, but it's not a function. And then we're going to be identifying functions in a moment. But then if you do have a function, it's possible that you could have a function that's one-to-one, a function that's onto, or it could be both, or it could be neither. Okay, these are just other specific ones, but it doesn't have to be either of these. So when we talk about one-to-one functions, a one-to-one function says that each element of the domain, so each x, pairs to exactly one unique element of the range, each y. So we already know for a function, all x values have to go to only one y value. They can't go to multiple y values. But what this really means is that no x value is paired with the same y value. So you can have a function where x values are paired with the same y value. But if that happens, it's not one-to-one. So to be one-to-one, every x goes to a different y value and only one y value. Then you can have a function that's called onto. And what this means is each element of the range, so each y, corresponds to an element of the domain. So ultimately, if you look at this diagram here, this is called a mapping diagram. Notice that all of the elements of your range are being used. They're all paired with an element in the domain. Unlike this one over here, this range value of C isn't paired with anything. So onto, if you want to make a note, this really means there's no, I'll call it like leftover y values. No y values that are not used or not paired with anything. And I do want to point out also, so I already said this one here, this one is not onto. Okay, and it's not onto because there's that element in the range, that C, that isn't paired with anything. So that's what something that isn't onto looks like. Then if I look at this mapping diagram, this one is onto, but this one is not one-to-one. My words kind of ran together there. That says one-to-one. So this one is not one-to-one. The reason why is, again, that element C, even though it's being used, it's paired with multiple x values, or there's two different x values that are paired with the same y value. So it's still a function, but it's not one-to-one. And then it just gives you an example of what it would be if both were true. So if it's one-to-one and it's onto. Every element of the domain is paired with an element of the range, or exactly one element of the range, a different one, and then each element of the range is paired with an element in the domain. So kind of one x value going to one y value. So with the following examples, and they continue on the next slide. So I have one example that's a set of ordered pairs, one example that is a graph, and one example that is a mapping diagram, just so you can see some different representations. So it says state the domain and range of each, determine whether it is a function first of all, and if it is a function, determine if it's one-to-one, onto, maybe it's both, or maybe it's neither. So if we look at example A, first of all, to find the domain, this is the set of all x values. Okay, and when we have ordered pairs, they're always in the form x, y. So when I'm writing this as a set, you should be using the braces, the curly brackets, to write a set. And I just have to list all of the x values that I see. If any of them repeat, you only have to list them once. So I have an x value of -6, -5, -3, -1, and +6. I happened to just list them in the order they were already in, and that happened to be numerical order. If it's not in numerical order, it's fine. It's nothing I would take off for if you didn't have them from least to greatest. So then the range, this is the set of all y values. And again, if any repeat, you only have to list them one time. So as a set, I have a y value of -1, a y value of -9, -7, +7, and then I have -9 again, so I don't have to write it a second time. I already have it. So then the first question is, after that, is it a function? That's what you have to determine first. And to be a function, I'm just going to make a note of something you can look for. Again, it means that every x value goes to only one y value. You don't have any x values that are paired with more than one. So how you would see that as a list of ordered pairs, it is a function if you have no repeated x values. Okay, if there's no repeated x values, that means it's a function. So if I look at my ordered pairs, every ordered pair has a different x value. None of the x values are the same. So yes, this is a function. If any of them were the same, it would not be. All right, and then if it is a function, so if I said no here, I would be done. Because if it's not a function, it can't be one of these two. These are only for functions. So since it is, now I determine is it one-to-one or is it onto. So one-to-one, this would be true. Again, like I had wrote up here, no x values paired with the same y value. So if you have no repeated y values, then it's one-to-one. Okay, but if I look at the ordered pairs that we have, I see that two of those ordered pairs have the same y value of -9. Okay, that means this is not one-to-one. So this is a no. If you kind of want to, I'll just kind of draw arrows up here as to why. I have two y values that are the same. So two different x values have the same y value. It's okay. It's a function. It's just not one-to-one. And the last one is onto. The only time you would say no for this is if you are given some sort of mapping, like in this example up here, where you can clearly see there's an element of the range that isn't being used. It's not paired with anything. So because all of our ordered pairs are all x's and y's paired together, this is a yes. This is onto. So the only time is if you are specifically told this is an element in the paired with anything. But you have to be told that. So some students kind of think of this as like a trick question. It's not meant to be a trick, as long as you understand it. Then it's not either of these if it's not a function. Yeah. Okay, are there any questions on that one? So we're going through the same, we're identifying the same things for the next two, but they're given in different forms. So the next one is given as a graph. Okay. So in B, what could I do? Because I want to identify domain and range. What's something I could do if I was given a graph to help me identify domain and range? Or as you're looking at this, what would you maybe do to go about finding domain and range? Carter? You could write out the coordinates. I could make this look like example A and write out all of these as ordered pairs. So if that helps you, you can do that. Okay, I'm going to start kind of in the leftmost here. And this is good review for naming and ordered pairs. Remember, make sure to name the x value first and then the y. So this one here, and you could write it next to them too. I'm going to write them off to the side. Is negative 3, positive 2. Is this one up here? Then I have negative 2, 1. I also have negative 2, negative 2. I have negative 1, 1. That's here. The one on the y-axis is 0, 2. And then 1, negative 2. Three, negative 3. And the one way up in the upper right is 4, 4. Okay, not all of you may need to do that. It might not be necessary for you personally to do that. But if that helps, you can write out the ordered pairs. Because now I can clearly see what my x values are and what my y values are to write the domain and the range. So domain as a set is x values are negative 3, negative 2. I only need to write it once. Negative 1, 0, 1, 3, and 4. And then for the range, I have positive 2, positive 1, negative 2. 1 repeats, 2 repeats, negative 2 repeats, negative 3, and then 4. If you were to write a value more than once, like if it repeats and you wrote it twice, I'm not going to take off for that, just so you know. But I'm just letting you know if it does repeat, you don't have to write it, 3 times if it's there. Okay, so is this one a function? I heard a no right away. Okay, we have 2 ordered pairs that have the same x value. So this is not a function. And that means we don't even have to look at one-to-one and onto, because if it's not a function, it can't be either of those. So then we're done. We can still identify domain and range for the relation, but it's not a function. Okay, and then C, so this one, the mapping diagrams are nice because it already tells you what the domain and range are. You just copy it down. So domain, I know has the values negative 3, negative 2, negative 1, 0, and 1. Range is 0, 2, 4, 6, 8. Okay, and I want you to realize also I could write this as ordered pairs as well. So how you would write these as ordered pairs, and maybe you want to do this, is the domain, this is your x values, range is your y, and your ordered pairs would be you look at the x value and you look at the arrow to see what y value it's paired with. So for example, 3 or negative 3, 0 is an ordered pair. Negative 2, 2 would be an ordered pair. Okay, so you could list those out if that is helpful to you. Is this one a function? I heard some yeses. If you look at your domains, just kind of look and see. There's only one arrow coming off of each x value, so it's not like one x value has a branch and it's paired with more than one. So yes, this is a function. Is it one-to-one? I heard a yes and a no. Look at this 6 here. I have two different x values that are both paired with 6 as a y value. That would be a repeated y value. So this is not one-to-one. Okay, because of that 6, that's why. So if you want to draw an arrow to remind yourself why is that if you're looking back at it, it's because of the 6. Is it onto? I heard a no right away. I have an 8 that's not being used. Nothing's paired with it, so this is not onto. Okay, so just giving you some different examples. They're represented differently, and then also they weren't all the same. They weren't all functions. They weren't all one-to-one. They weren't all onto. Any questions on those right now? Okay, so then some more vocabulary to go on with this. There's two different types of relations: discrete relations and continuous relations. And it's easiest to identify them by their graphs, but a discrete relation is a relation in which the domain is a set of individual points. So the graph would consist of points that are not connected, like this graph A here would be discrete. Continuous is a relation in which the domain has an infinite number of elements, and it can be graphed with a line or a smooth curve, like graph B. Now notice this comes more into play when you are graphing yourself. So notice all of these points, they do appear to form a line. It's when you have to decide, do you actually draw a line through them? Do you connect them or do you leave them separate? So that kind of depends on what your x and y variables stand for. Does it make sense to connect them? Or would it make sense to leave them separated? And there's practice with that. We'll go through an example. But that's more for you to determine. But if I ask you, for example, to sketch a discrete relation versus continuous, you should know a discrete relation does not have a line or smooth curve connecting the points, and continuous does. And then the vertical line test, I know you've seen this before. When you have a graph, like we could actually have used this in example B. When you have a graph, you can determine using the vertical line test if the relation is a function. So it's right here. If no vertical line intersects a graph in more than one point, the graph represents a function. So that gives you an example of a parabola. The dashed line just represents one vertical line, but if I draw a vertical line through any part of my graph, I'm only going to cross my graph one time. And if that's true, it's a function. If I cross through it more than once, any given vertical line, like in this one when the parabola is sideways, that vertical line touches it twice. Then it's not a function. So I could have gone up here if I look at B. When I draw in this vertical line here, so if I drew in that line, that would be the line x equals -2. It's through the x value -2. Notice that one line goes through two different points. So graphically, it tells me that it's not a function, which we had already determined. But just so you can see two different ways to determine in that example if you have a function or not. So when you do hit more than one point, it means you have repeated x values. That's another way to look at it. Okay, so then what I'd like to get through here, looking at example 2. We can also have relations and functions represented by equations. And usually if it's given as an equation, it's a little harder to identify if it's a function just by looking at the equation. So you can graph that equation on a coordinate plane and then use the vertical line test to determine if it's a function. So if we look at example 2, it says to graph y equals x squared plus 1. It does say to determine the domain and range. It says determine whether it's a function, one-to-one, onto, could be both or neither. It also says to determine if it's discrete or continuous. So a lot of things we're identifying here. First of all, to graph a function, one thing I want you to remember is you can graph any equation by making a table. So I know some types of equations and functions have shortcut ways to graph them. Like lines, you can use the slope and the y-intercept. But remember, you can always graph. If you're looking at a function saying, I don't remember how to graph that, make a table, make an XY chart, whatever you call it. So here I can choose any x value I like, substitute that into the equation to get the y value. So I'm just going to substitute in, I'll do -2, -1, 0, 1, and 2. You don't have to have 5 points. I'd say if you don't know what the graph is going to look like, having 3 or 5 is probably good. If you can always get points, and then if you need more, graph more. So if I plug in -2 for x, -2 squared is +4 plus 1 is 5. If I plug in -1, you could also use a calculator if you need to, depending on the function. -1 squared is +1 plus 1 is 2. If I plug in 0, 0 squared is 0, plus 1 is 1. If I plug in 1, 1 squared is 1, plus 1 is 2. And then if I plug in 2, 2 squared is 4, plus 1 is 5. Okay, and then I can plot these as ordered pairs. And I am going to see that this is going to make a U. This is a parabola. So you might recognize anytime you have a function where the highest exponent on x is a 2 when you have an x squared, that is quadratic. So you did cover those in Algebra 1. We'll review them in Algebra 2. But it is quadratic. All quadratic functions, their graph is a parabola that either opens up or opens down. So with this one, domain and range are a little bit different than how we identified it with the other examples, because I know I have 5 x values here, but these are not the only x values that I could possibly have. I could have plugged in -10 if I wanted to. I could have plugged in 22 and a half if I wanted to. So the domain is really x could be any number I want it to be. And the fact that this graph does continue, it not only continues up, but it continues out. So it's like up and out. So that means every single x value would be a part of the domain. And we call that all real numbers. So the domain, I'm going to show you the set builder way to write it. So you have a brace, domain is x values such that, and this is how we would write it, it's x, and then it's a fancy looking E. It's like you make a C and then put a line so that it looks like an E. And then the all real number symbol is a capital R, but it has that double stem to it. So the domain is all x values such that x is an element of all real numbers, is what that means. I want to show you the set builder notation. If, as long as you understand it's part of all real numbers and you have the all real number symbol, you're okay. The range is different. If you look at your y-axis, so look up and down on the graph, notice the lowest point is at the y value 1, and the graph doesn't exist below that. So for y values that are less than 1, the graph doesn't exist. all of the y values are either 1 or higher. So I could write this as in set builder, the values y such that, and I'm going to write an inequality, the y values are greater than or equal to 1. That's for this graph specifically. It doesn't mean all graphs will have a range like that. Some graphs do have a range of all real numbers. Okay, now looking at this, would you say this is a function? I see some nods, I hear some yeses. So you could either look at the table you made, or as we talked about, if you plug an x value in, you're not going to plug one x value in and get two different y values. But you could also use the vertical line test. Any vertical line would only intersect it once. So I'm just going to put yes, it's a function. So yes, function, or function yes, however you want to notate that. Would you say this is 1-to-1? No. The y values, even look at your table, y values are repeating. So this is not 1-to-1. Would you say it's onto? This is the one students think is a trick, but I do see some nods. We are not told, hey, -8 is actually in the range, but our graph never touches it. It's not being used. So if you have to make a graph yourself like this, it's onto. So this is yes onto. Unless you are specifically given the range, like we were in the very last example we did. You're given the range and you're told something is in it and you don't see it being used, then it's onto. And then, let's see here. What am I forgetting? Oh, is it discrete or is it continuous? So when we graphed this, we had made the choice after I plotted those points. I made the choice to connect them with a smooth curve. The reason being is I could have plugged in, if I wanted to, -1.5. I would get a y value if I did that. I could have plugged in 0.75 if I wanted to. So x could be anything, and that means it's continuous. I connected them with a smooth curve. If I was told x can only be these numbers and any other number doesn't make sense, then it's discrete. So this is